Hello, this is the Code Critics. In this episode, we will learn how to quickly and easily create Python packages. There are three main reasons why we need Python packages. First, when your project increases in size, with more and more code files that depend on each other, at some stage, you will encounter ModuleNotFoundErrors when importing. Python packages eliminate this problem. Secondly, Python packages provide namespaces, which avoid potential name conflicts caused by function or class names already used by other packages. Finally, Python packages allow the easy transfer of code to other computers or users. Before we dive into the details on how to create a Python package, let's get one thing out of the way first. And that is the horrible hack that is often recommended to fix the ModuleNotFoundError. When calling import of some module, Python searches the Python path to find the requested Python module, and if it cannot be found, a ModuleNotFoundError exception is raised. The number one recommendation on the internet is therefore to add the project directory to the Python path, either within Python itself or via a shell script. Never ever do this. It is a terrible hack that works in the short term, but causes all kinds of problems in the long run. Most importantly, it guarantees that the code runs on one machine in a fixed location only, but nowhere else. Just don't do it. There is an easy, fast, and much better way that not only solves the ModuleNotFoundError, but also addresses the two other reasons mentioned before. And that is to create a Python package with a setup.py script. As an example, let us assume we want to implement a scientific calculator. The file or package structure could look like this. We have a folder that represents the GitHub repo with the entire code. Names for GitHub repos should be lowercase, can contain hyphens, but should not contain underscores. Here we pick sci-calculator as repo name. Within the GitHub repo, there must be a subfolder that represents the Python package, here named scal. The repo and the package could have the same name, but don't have to. Package names should be short, lowercase, and should not contain underscores and cannot contain hyphens. The emphasis is on a short package name, since long names result in unwieldy imports. That's why it's NumPy and not numerical Python, for instance. A Python package is simply a folder on the file system. And Python needs a marker file with the name __init__.py to recognize folders as Python packages. Apart from a version number, more about that later, init.py should not contain any code, with a few exceptions. Any file with Python code within a Python package is called a Python module. In this example, calculator.py is a module. A typical package also contains a .gitignore file, a readme file, and a license file. All of those ones are generated automatically when creating a GitHub repo via the web interface. Finally, we come to the most important part, the build script setup.py. Note that setup.py is not located under the folder scal, but at the base of the repo. Setup.py is what makes the Python package installable. For instance, if we call python setup.py install, the scal package will be installed and can then be imported. Note that the import path to import functions from the calculator module would be scal.calculator, assuming that we have functions such as add and mult implemented in calculator.py. So, what's inside the build script setup.py? Here an example. As you can see, the only thing that setup.py does is to call a function setup, imported from setup tools, with some parameters. First is the name of the package. Any string would work here, but the folder name of the package and the name in the setup should match. To avoid any mismatches, we import our ascal package and then call ascal.__name__, which contains a string with the package name. In a similar fashion, we set the version of the package. In __init__.py, we define a constant __version__ that contains the version number. When importing a package, all code in init.py is executed, and we therefore can access the version number by calling ascal.__version__. This, by the way, is the expected method of Python packages to report their version number. Import the package and access __version__ to retrieve the version number as a string. As for the format of the version number, the recommendation is to use semantic versioning, where a version number is composed of 3 parts separated by dots. The first number is the major version. If there are changes to the code that are not backwards compatible, the major version is incremented. The second number is the minor version. If new functionality is added, this number is incremented. And the third number is the maintenance version, where bug fixes are tracked. Next, we set some non-essential information such as author email, description, and the repo URL. The packages parameter is set by calling findPackages, which locates all modules in all subpackages of our ascal package. FindPackages can be fine-tuned to include or exclude certain packages. Note that using FindPackages is the correct and robust way to avoid ModuleNotFoundErrors, not hacking the Python path. If the code requires a specific Python version, this can be stated in the Python requires parameter. The specification is very flexible here and allows to define ranges of versions and the exclusion or inclusion of specific versions. Finally, and most importantly, we list all Python packages with their versions that our ascal package depends on. These dependent packages will be automatically installed when the ascal package is installed. The specification of the package versions is again very flexible, but in general, greater or equal than is used, which allows newer packages to be used and to be updated. You can run pip list to find the versions of the currently installed packages. Note that you don't want to add all the packages pip list returns, only the ones your package is actually importing. Installing our scientific calculator package on a different computer is now very easy. We clone the repo and run setup.py. There are 2 ways to run setup.py, with the flag install or the flag develop. Install is the standard method, which essentially copies the package folders and files to a folder named site packages. You can find out where that folder is by running get site packages. Develop is the setting you use when implementing the package. It only creates a link inside packages that points to the location of the repo. This has the advantage that during the development of the package, there's no need to reinstall when the structure of the package changes. So instead of hacking the Python path to fix ModuleNotFoundErrors, we simply create setup.py, run python setup develop, and that's it. It is the recommended method and gives us an installable package with a version number and defined dependencies. When reading up on installable packages and package dependencies, you will come across an alternative method to setup.py that uses a file usually named requirements.txt. Technically, install requires in setup.py and requirements.txt are doing the same. They allow to specify depending packages and their version numbers. Their intent or purpose, however, is very different. Requirements.txt makes a strong promise. If you install the exact versions of the dependencies listed in requirements.txt, this code will run. Usually, requirements.txt is created by calling pip freeze, which copies the names and exact versions of all packages installed in the current environment into requirements.txt. A pip install of requirements.txt will replicate this environment as precisely as possible. But since Python packages are often wrappers around C++ libraries, there still might be differences depending on operating systems and computers. So requirements.txt makes a very strong promise, but the promise is not 100%. Install requires, on the other hand, usually allows dependencies with a minimal version or newer, which means it encourages the update of packages, for instance for security patches. It does not promise that package updates do not break the code, and therefore usually some test harness such as unit tests is added to ensure the correct function after updating. While setup.py appears weaker than requirements.txt, it is actually much better. It gives us a package with version numbers that can be installed in many different environments, with dependencies that can be updated. Requirements.txt is generally too restrictive and requires a virtual environment to run in. With a few exceptions, I strongly recommend not to use requirements.txt. To summarize, first, never ever hack the Python parse to fix ModuleNotFoundErrors. Instead, create proper Python packages with setup.py. It usually only takes a few seconds and works reliably. Make sure to add and maintain a package version number, preferably in semantic format. Only this way you can identify the version that is installed on the user's machine, should there be a problem. On the user's machine, use setup.py with the install flag, while during development of the package, use setup.py with the development flag. Finally, don't use requirements.txt, but use install requires in setup.py for dependency management. I added some links to template repos for Python packages in the description. And that's it. Thank you for listening.